The first sign is not fire, not violence, not even noise. It is silence, an unnatural, system-wide silence that spreads faster than panic ever could. In a modern American city, infrastructure is not just support. It is life itself, an invisible network of synchronized systems that maintain water pressure, regulate temperature, move food, and coordinate emergency response. When that system fails, the danger is not immediate chaos, it is the sudden absence of control. In cities like Phoenix, Houston, New York, New Orleans, Los Angeles, Chicago, and Miami, the threat does not come from a single catastrophic event, but from the cascading failure of tightly coupled systems designed for efficiency rather than resilience. The danger begins with dependency. Urban populations operate on what engineers call just-in-time logistics, where resources such as food, fuel, and medical supplies are delivered with minimal storage buffers. This creates a fragile equilibrium. When infrastructure fails, whether through power grid collapse, water system contamination, or transportation disruption, the supply chain does not slow down, it stops. The misunderstanding most people carry is that cities are inherently robust because of their size and resources. In reality, scale amplifies vulnerability. A disruption that might inconvenience a small town can destabilize a major city within hours because millions depend on the same synchronized inputs. The hidden science lies in interdependency. Electrical grids power water treatment plants. Water systems cool power stations. Transportation networks deliver fuel to both. This interconnected design increases efficiency but creates what systems analysts call cascading failure potential. For example, in a city like Houston, widespread flooding does not just damage homes. It disables substations, halts fuel distribution, and contaminates water supplies simultaneously. Evidence from past disasters shows that once two or more critical systems fail together, recovery time increases exponentially, not linearly. Emergency management models consistently demonstrate that after 72 hours without stable infrastructure, urban environments begin to experience systemic stress. Hospitals exceed capacity, law enforcement response times degrade, and public order becomes increasingly difficult to maintain. The survival implications are often misunderstood because people focus on the visible threat rather than the invisible timeline. The real risk is not the initial event, but the delay in restoration. In Phoenix, extreme heat transforms a power outage into a mass casualty scenario within hours due to the body's limited ability to regulate temperature without cooling systems. In New York, the vertical nature of living, high-rise buildings dependent on elevators, pumps, and electronic access, turns a blackout into a logistical trap, isolating thousands without water pressure or mobility. These are not hypothetical risks. They are predictable outcomes derived from engineering constraints and human physiology. As the situation escalates, behavior shifts. At first, there is compliance and patience, a belief that systems will recover quickly. This is followed by improvisation, where individuals begin to secure resources independently. The transition from cooperation to competition is not driven by morality, but by perceived scarcity. Studies in disaster psychology reveal that when individuals believe resources are limited and resupply is uncertain, decision-making becomes shorter-term and more risk-tolerant. This is where cities like Los Angeles and Miami become uniquely vulnerable, not because of population alone, but because of geographic constraints. In Los Angeles, reliance on imported water through aqueduct systems means that any disruption to those channels creates immediate shortages. In Miami, low elevation and saltwater intrusion can render freshwater systems unusable during storm surges, accelerating the collapse of potable water access. The next phase is system strain turning into system failure. Chicago's dependence on rail and trucking corridors means that if transportation halts, food distribution falters rapidly despite the city's central location. New Orleans, already below sea level, relies heavily on pumping systems to remain habitable. Failure of those systems transforms infrastructure collapse into environmental threat. The misconception is that federal or state intervention can immediately stabilize these situations. In reality, response logistics are constrained by the same failures affecting the city. If roads are impassable, fuel is scarce, or communication networks are down, external aid cannot scale quickly enough to meet urban demand. Hidden within this progression is a critical scientific principle: redundancy determines survival. Cities optimized for efficiency often eliminate redundancy to reduce cost, meaning there are fewer backups when primary systems fail. This is evident in power grids with limited islanding capability, water systems without decentralized treatment, and food supply chains lacking local storage. Evidence from infrastructure resilience studies shows that cities with higher redundancy recover faster and experience lower casualty rates, regardless of the initial disaster severity. However, most major U.S. cities prioritize throughput over backup capacity, making them highly efficient under normal conditions and dangerously exposed under stress. The implications for survival are not abstract, they are immediate and personal. Without power, communication networks degrade, cutting off access to information that guides decision-making. Without water, sanitation collapses, increasing the risk of disease outbreaks within days. Without transportation, evacuation becomes nearly impossible, trapping populations in deteriorating conditions. Each layer of failure compounds the next, creating a feedback loop that accelerates instability. This is why infrastructure collapse is not a single event, but a process, one that unfolds with increasing speed once critical thresholds are crossed. As the system continues to degrade, the city itself begins to change function. What was once a network designed for movement and distribution becomes a series of isolated zones, each with varying access to resources. The risk is no longer evenly distributed. Some areas retain partial functionality, while others experience near-total collapse. This uneven degradation creates migration pressure within the city, as individuals move toward perceived resource hubs, further straining those areas. Emergency management data shows that this internal movement often precedes larger-scale displacement, signaling a transition from infrastructure failure to humanitarian crisis. And it is at this point, when systems are no longer failing independently, but collectively reinforcing collapse, that the true danger emerges, not as a sudden event, but as an irreversible shift in how the city operates, where survival is no longer supported by infrastructure, but determined by how quickly individuals recognize that the system they depended on is no longer coming back online. What follows is not recovery, but acceleration. Once multiple systems fail simultaneously, the timeline compresses in ways most people are not prepared to recognize. The danger is no longer defined by the initiating event, but by the speed at which secondary failures begin to stack. In cities like Phoenix, the loss of power does not simply remove air conditioning. It eliminates the electrical backbone required to pump water, operate hospitals at full capacity, and maintain fuel distribution. The analysis reveals a critical threshold. When energy availability drops below operational demand, prioritization begins, and not all systems are restored equally. The misunderstanding is the assumption that essential services are restored in parallel. In reality, infrastructure triage occurs, and certain areas or functions are deliberately deprioritized to stabilize the whole. The hidden science behind this lies in load shedding and system balancing. Electrical grids are designed to prevent total collapse by cutting power to specific regions when demand exceeds supply. This controlled failure is intended to protect generation assets, but in densely populated cities, it creates pockets of complete outage that can persist for extended periods. Evidence from previous grid disruptions shows that these outages disproportionately affect areas with older infrastructure or higher load density, compounding existing vulnerabilities. The survival implication is stark. Location within a city begins to determine outcome more than preparedness alone. Those in high-rise buildings without backup generators face immediate water loss as pressure systems fail, while those in ground-level structures may retain minimal access for longer. As this imbalance grows, behavior adapts under pressure. The escalation is not immediate disorder, but a gradual erosion of predictability. In New York, for example, the vertical dependence on elevators and electronic access systems transforms buildings into containment zones. Residents above certain floors become physically isolated, unable to transport water or supplies efficiently. The misconception is that urban density provides safety in numbers. However, density without function becomes constraint. The more people concentrated in a non-operational system, the faster resources are depleted and the harder movement becomes. In Houston and New Orleans, water becomes the dominant variable. Flooding or pump failure introduces a dual threat: physical displacement and contamination. The hidden principle here is that water systems are not designed for rapid purification under compromised conditions. Treatment plants require stable power, chemical inputs, and controlled flow rates. When any of these variables are disrupted, water safety cannot be guaranteed. Evidence from past events indicates that boil water advisories often come too late or are ignored due to lack of fuel or functional cooking methods. The survival implication extends beyond thirst. It includes the rapid onset of waterborne illness, which can spread quickly in dense populations with limited sanitation. Meanwhile, in Los Angeles and Miami, geographic constraints intensify the crisis. Los Angeles depends heavily on imported water delivered through long-distance aqueducts. A disruption anywhere along this chain reduces supply across the entire metropolitan area. Miami faces a different but equally severe limitation: saltwater intrusion. When storm surges or rising sea levels infiltrate freshwater systems, the contamination is not easily reversible. The misunderstanding is that proximity to water ensures availability. In reality, potable water requires infrastructure, and when that infrastructure fails, abundance becomes unusable. The escalation continues as transportation networks degrade. Chicago's role as a logistics hub becomes a liability when rail lines and highways are disrupted. Food distribution depends on constant movement, and without it, retail inventory depletes rapidly. The hidden science is inventory turnover. Most urban grocery systems operate on cycles of days, not weeks. Evidence shows that within 48 to 72 hours, shelves are empty, not just from panic, but because surplus is never stored. The survival implication is clear: access to food becomes a matter of timing, not supply. As resources tighten, internal migration intensifies. People move toward perceived aid centers, creating localized surges that overwhelm already strained systems. The misconception is that centralized aid stabilizes populations. In reality, it accelerates depletion and creates new failure points. Data shows decentralized access reduces strain, but most cities are not designed for it. At the same time, communication breakdown adds another layer of risk. Without reliable information, people rely on assumption, often inaccurately. The hidden principle is that information is a survival resource. When communication fails, coordination collapses, and misinformation spreads faster than verified updates, increasing exposure to danger. Under this compounded stress, the system begins nonlinear collapse, where small disruptions trigger disproportionately large consequences. The city shifts from degraded function to systemic instability, where recovery depends not on fixing parts, but restoring interconnections. The implication is stark: survival is no longer about enduring the initial failure, but navigating what comes after. As these effects converge, temporary disruption turns into structural collapse, and the city ceases to function as a unified system, becoming instead a fragmented environment where survival depends on adapting to the absence of infrastructure.